A very good morning to all the participants present here today. I am Navami Bhuya, Department of Geography, Lakhimpur Girls College, North Lakhimpur. Dear friends, I would like to welcome you to today's webinar on application of remote sensing and GIS in earth science. This lecture is a part of the series of online lectures organized by IQAC Lakhimpur Girls College. During this uncertain period of traditional teaching and learning process due to the global pandemic situations. At the very outset, I would like to introduce before you our resource person, a young scientist of 30 years of age, Dr. Ashim Sattar. He is currently residing in Ohio, USA, doing his postdoc in University of Dayton. Dear friends, Dr. Ashim Sattar, originally from North Lakhimpur, is a permanent resident of Guwahati, where he did his schooling. After that, he went to University of Mysore to do his graduation in geology in the year 2011. From the same university, in the year 2013, Dr. Sattar did his master's in applied geology and stood first class first with distinction marks and won 3 gold medals for his academic excellence. Dr. Sattar achieved a reward called Nehru Grimson Fellowship in 2014 and joined in an student exchange program to study in the University of Iceland, from where he again passed out with first class. In 2019, Dr. Sattar was awarded PhD on remote sensing and glaciology from IIT Roorkee, which he did as DST Inspire Fellow. Currently, he has been doing his postdoc from the University of Dayton, Ohio. His teaching and research experiences include he worked as assistant professor in NIIT University, as JRF in Kanpur IIT, IIT Roorkee, as SRF in IIT Roorkee, as project assistant in IISc Bangalore. He has many publications, out of which 6 numbers of publications in peer-reviewed journals with impact factor as high as 5.589. He has presented papers in 7 international conferences and 3 national conferences. There are 4 numbers of scientific modeling expertise credited to Dr. Ashim Sattar. They are glacial lake outburst modeling, glacial dynamics ice thickness modeling, glacial velocity modeling, hydrological modeling. Dr. Ashim Sattar is specially trained in geological map techniques, geochemical analysis using advanced instrumental techniques. He did 2 numbers of GIAN courses, one in climate change impact analysis from IIEST Kolkata and the other in Glacier and Water Resource Management Global Initiative for Academic Network, which he did from JNU Delhi. His field experiences include DGPS glacial lake mapping in the Himalayas, GPR survey, glacial moraine sample collection for dating from above 4,500 from mean sea level, LULC validation for modeling. Dear participants, in a nutshell, I have put before you a very short introduction of Dr. Ashim Sattar. Now, before we hear from our resource person, I would move on to the next program in agenda, for which I shall request our respected principal, Sir Dr. Surojit Bhuya, to deliver his inaugural speech. Over to you, sir.
Good morning to all of you. First of all, I would like to welcome all of you to this webinar organized by IQAC of Lakhimpur Girls College. And this is, in fact, lecture number 10 of this webinar series organized by jointly IQAC and Department of Geography of this college. So today we have with us Dr. Ashim Sattar. He is postdoctoral researcher from University of Dayton, USA. And we are very much thankful to you for giving your valuable time with us. despite of your busy academic schedule. And he will give a talk on applications of remote sensing and GIS in earth sciences. Nowadays, remote sensing is emerging as a popular tools for preparing map, and the GIS is used for storage, retrieval, and analysis. And in these days, people are using these two tools to project about the spread of the COVID-19 in various states, in various parts of the country. So I think it is a very important topic. I thank Department of Geography of this college for organizing this webinar, and I think the participants will be benefited from this. And with these few words, I would like to declare this session open. Thank you.
Thank you very much for the kind introduction. Thank you. First of all, I'm really delighted to be here and to see so many participants. It's almost 165 participants right now who is listening to me, and really excited to talk about the topic which I have chosen to speak on, that is application of remote sensing and GIS in earth sciences. And as already mentioned in the introduction, I have been working on glacier-related hazards in the high mountains of India, that is the Himalaya, where I have used remote sensing as the major tool and different modeling techniques to study glaciers. And during my postdoc here at University of Dayton, I am working on a NASA-funded project in which I have to look into the glacier hazards, again using different modeling techniques and remote sensing and GIS as primary tools. And yes, not to forget about this whole situation. We are all going through a tough situation right now with the pandemic affecting over many people, many thousands of millions of people around the world. And I really appreciate the fact that IQAC and LG College has put forth this webinar series. And I think all of you are taking the forefront to take proper care, and also taking care of your loved ones, your family. So with this short introduction, let me start with my topic, that is remote sensing. So before I start, I want all of you to grab your attention to the image that you see right now in the backdrop. I think most of you are familiar with the place which has been shown in the picture right in the first slide. So let me remind you, this is the Brahmaputra River, which is basically crossing through the city of Guwahati. You may see, I'm sure if you can see my cursor. Is my cursor visible to you? Could you please confirm me?
Yeah, it's visible.
Yes, it is visible.
Okay, so you may see the mighty Brahmaputra River, which is flowing across the city of Guwahati. If you see my cursor, this is city of Guwahati. This is the place where I come from. I have done most of my schooling in Guwahati. Me coming originally from North Lakhimpur, where LG College is located. I'm happy to interact with all of you today. So let me start with the first slide here. Well, the topic says that I'll be broadly talking about earth sciences. What is basically earth science? It is nothing but the branch of science which deals with basically anything which is related to the earth, its atmosphere, its surroundings, And if you see the broad branches of earth sciences, it is basically divided into 4 major branches, which is meteorology, which deals with the atmosphere, the weather conditions, the climate conditions. And then you have the geology, which is basically the study of the earth surface, its interiors, right from the surface towards the mantle and the core. Then comes the major branch, which is called the oceanography, which deals with the surface water, the oceans, the marine ecosystems, and how these water interact with the land, the terrestrial ecosystem. And astronomy. Astronomy is the outer space, which in this branch, the relationship between the extraterrestrial bodies with the Earth is established. So all these can be a part where remote sensing can be used to analyze and make decisions and study them. And if you see my cursor, where I will be mostly highlighting the career pathways of geology. So I'm sure many people here in the audience are geologists, and they mostly have chosen geology as their career. So I'd like to put a glance upon remote sensing. If you see the red, the part where I have highlighted with a red dotted line here. So remote sensing is almost connected directly or indirectly to every branch of earth sciences or geology. If you see, remote sensing is directly connected to natural hazards. It is indirectly connected to geophysics, planetary sciences, petrology, geochemistry, geochronology, sedimentology, geomorphology, surface processes, engineering geology. So this is an endless list where you can just use remote sensing as a tool to study all these broad subjects of earth science. To come about the most popular definitions we have for remote sensing, one of them was given by Sabins in 1996, which says that remote sensing is the science of acquiring, processing, and interpreting images that records interaction between the electromagnetic energy and matter. Another popular definition, which is given by the UN in 1999, tells remote sensing is nothing but the sensing of the Earth's surface from the space by making use of properties of the electromagnetic waves emitted, reflected, and diffracted by sensed object for the purpose of improving natural resource management, land use, protection of the environment. Well, the most common definition of remote sensing and widely known definition is given by Lilsand and Kiffer in 1994, which states that remote sensing is a science and art of obtaining information about an object, area, phenomena through the analysis of data acquired by a device which is not in contact with the object, area, phenomena investigation. So now let me quickly explain you what is the working principle of remote sensing. If you see the image on the top right, this tells you about the basic principle of how remote sensing works. Mostly for remote sensing, you need to have a source of energy. If you see on the top right, which shows the sun as the major source of energy, then you have the Earth's surface processes, or the Earth's surface, which we are interested to have to gain information, and we have a sensor, which can be any sensor from satellites to handheld GPS to thermal guns, etc. So what remote sensing does is that when the sun emits energy in the form of electromagnetic radiation, it makes its way through the upper extraterrestrial atmosphere, enters into the Earth's atmosphere, interacts with the surface. So during this process, most of the radiations are mostly absorbed at some point here in the upper atmosphere. Some of the radiation gets scattered at some places. Some of those radiation strikes the Earth's surface and reflected back to the atmosphere again, which this reflected energy can be sensed by another object, which is called the sensor, and then utilizes the information to gather fruitful information about the surface. So another very, very common example of Earth remote sensing can be the human eye. We all know we can see things. So what does it do? When you are illuminating certain object and you are looking at it, so the energy which is falling on the object is reflected back to your eyes, and that is how you are able to see things. So imagine a dark room. Will you be able to see anything? No, because there is no source of illuminance. There is no source of energy. So once you switch on your light, the light falls on the object and you will be, so basically your eye is the sensor, sun or any kind of light form is the energy, the object is what you are interested in, and the signals that your eye receives is given to the brain. The brain processes the signals, which helps you make a decision. For example, if you're looking at a cup, you send your signals from the eye to the brain, telling it that it is a cup, or it is a bottle, or it is a TV. So that is the same principle how remote sensing works. Well, when we talk about scientific data collection, most of the scientists, what they have to have is the preliminary data sets based on which they try to interpret things to come to a proper decision. So the data can be collected multiple ways. One of the ways is called the in situ collection, which means you collect data on the field from the location where the object of interest exists. And the other way is to collect information remotely. So if you see the diagrams here, you see two people, mostly geologists. If you can see the hammer and the rocks, these are geologists going to the site location, collecting samples. This is in situ measurement. You have been to the field, collecting samples, and then bringing the samples for various different analysis, maybe lab analysis or spectrometry analysis, and so on. Whereas you can see the mighty Himalayas here with the glacier, which is captured by, these pictures are captured by one of my colleagues, which is Greg Leonard. These are, he's been to the field, captured photos of the glaciers. You may see how the Himalaya looks like. All these are in situ data collection. And if you see on the left, these are remote sensing images. On the cursor I'm pointing at is a water body. This is a lake, and it is captured by the satellite. And you can see how the lake has grown over the years from 1975 to 2017. So this temporal analysis can also be done with the help of satellite images. On the backdrop, I have another image which shows the thermal image of Dayton, Ohio. This is the place where I currently reside. So these are remotely sent satellite images. So we haven't been to the field to collect this data, rather use the products of the satellite, which actually is remotely sensed. So now, what are the benefits or the advantages and disadvantages of these methods? Whether we should collect the data in situ, going to the field, or whether we should use remote sensing techniques to acquire data for scientific analysis. Well, to answer this is quite complicated, but yes, quite easy also, because remote sensing has a greater advantage, because in situ measurements can lead to observer errors, and limited coverage. So you cannot cover the entire say suppose you want to do a survey in an area which is 100 square kilometers, and you personally going there and collecting data of at each point becomes really difficult. And maybe you need to go there several times so that you can complete your survey. But again, in temporal analysis, you may use different techniques. So what happens, there is an inconsistency of the techniques. So the results of one survey might change from the other survey and becomes incomparable. Whereas the same data, for example, if you see the image here, you can see a person collecting the data from the plants using some spectrometer or thermal gun or a moisture meter. It can be anything. And you may see in the photo which has been shown, this is myself here standing with a DGPS rover. And this was my field work during 2018 when I was doing my PhD. This is near the JP Dam in Uttarakhand. It's almost in a height of 3,500 meters above mean sea level, quite close to Badrinath, where I had to do some field work. Because using DGPS, I could accurately measure points, but not a greater or a larger size in area. Similarly, the same data can be collected remotely. So if you see the difference between these two pictures, both the top pictures are showing a volcano, where in one of those volcanoes, you can see that some of the people are trying to collect the temperature or collect samples manually, whereas on the second device, on the second photo, you can see a person is trying to remotely determine the temperature of the lava using a thermal gun. You may see she or he holding a thermal gun and trying to see the temperature of the lava. So both of them are doing the same thing, but using different methods. So again, if you see the images below, this is me standing with the DGPS rover, where I've been taking measurements of the lake. Behind me, you may see a water body. This is the Satopant Lake, which is located around 4,000 meters above mean sea level. I was there in 2018 for my research, and the same lake can be also seen in a satellite image, and it has broader view. I cannot show the entire lake here because the scale matters, and a satellite image is capable of covering larger area, covering the whole lake, where I can just collect data from single points or limited area. So these are some of the advantages and disadvantages, but both methods stand alone. Well, again, let me quickly glance through this image. Again, I've told you that the source of energy is the sun. As the energy is released or emitted by the sun, as it makes its way through the atmosphere, it gets scattered by clouds or atmospheric gases, and some part of it reaches the Earth's surface, where you have the different components like vegetation, urban areas, and it gets reflected back to the satellite, which is the sensor, and it basically processes the signal which is reflected back. To make a note here is that every single entity on the Earth's surface has its own characteristics. A reflected ray from the vegetation would not be similar to a reflected ray from an urban area, or a reflected ray from the soil will be different from a reflected ray from the vegetation. So every phenomena or every component on the Earth will have their own signature while interacting with this electromagnetic radiation. So, well, electromagnetic radiation, to define, it is nothing but it is a form of energy, a source of illuminance which illuminates the target, reflected back, and it can be characterized. Electromagnetic radiations basically can be characterized using two two properties, that is the wavelength and the frequency. So what is wavelength and frequency? We all know in our basic physics classes. We have the wavelength is nothing but any electromagnetic radiation will have a magnetic field and an electric field which will move along a direction, and both these fields will be perpendicular to each other, and the wavelength is defined as the distance between the two crests or the two troughs of the wave. For example, here in this figure, if you see, this is a crest, the same wave has a trough here and it goes down up again, and you have another crest. So the distance between one crest to the other crest or one trough to the other trough is the wavelength. And frequency is nothing but the number of cycles per unit time. The number of cycles, the number of crest or trough passing through a single point per unit time is given by it's called the frequency. So this is again, C is the speed of light, E is the electric field, M is the magnetic field. Both has a perpendicular relationship. Moving on, electromagnetic waves, as I said, are not equal. They vary both based on its wavelength and frequency. Some part of the electromagnetic waves may have broader wavelengths. Some of them can have moderate wavelengths. Some of them have shorter wavelengths. And how does the frequency vary? So we have a relationship between the wavelength and the frequency. So the wavelength is generally denoted by the letter lambda. So let us see how these two properties are connected. So before we go, let us quickly go through the measurements. How do we measure wavelengths? Wavelengths are generally measured in meters, and also some factors of meters such as nanometers, micrometers. Some of the wavelengths can be very, very small and can be centimeters. So let's look into how these two properties are connected. Here, there's a relationship which says that C equals to lambda V, where C is the speed of light, and lambda and V are wavelength and frequency respectively. So you may say that wavelength and frequency are inversely proportional. So a shorter wavelength, the higher is the frequency. The longer wavelength, the lower is the frequency. So understanding the characteristics of electromagnetic radiation in terms of their wavelength and frequency is crucial in understanding the information to be extracted from remote sensing data. So whenever we are using remote sensing, we should see that every target that we are trying to gain some information will react differently based on their characteristics of the reflected radiation and its frequency and wavelength. So we always get confused when we are looking into electromagnetic radiation. What is the size? How does it vary? Which part has the maximum energy? Which part of the electromagnetic radiation has the minimum energy? What is the source of these different parts of electromagnetic radiation? So this is a very comprehensive view where you can see every wavelength. For example, if you see my cursor, from the longer wavelengths to the shorter wavelengths, we move from radio waves to gamma rays. From radio, microwave, infrared, visible, then comes the X-rays and the gamma rays. So if you see the wavelengths, the radio waves has the maximum wavelengths. The distance between each trough is higher as compared to the other energy levels like the microwaves, infrareds, or X-rays. And if you compare the size of these wavelengths, you must be thinking, how big can these wavelengths be? So if you see that a wavelength of a radio wave can vary up to a soccer field or a house. So these has very, very long wavelengths, and they have the property to travel longer distance and have low frequency. Whereas if you go towards the shorter wavelengths, the wavelengths can be as small as a water molecule or a bacteria or a virus. So, but again, as we move from the longer wavelengths to the shorter wavelengths, the energy increases. So radio waves have lower energy. If you see the lower bar here, the bottommost scale, which tells you about the energy. So the longer frequency has lower energy, whereas shorter has higher frequency. And these are some of the sources. For example, the FM radio gives that we listen to every time we drive a car. We have the FM and the radio, which gives the frequency monitoring radio, which basically operates on radio waves. We have the microwave, which we use to heat our food almost in our daily routine. The radar for communication purpose uses microwaves. Infrared, sometimes our body can also give out heat in the form of energy, which is also a part of thermal energy. Then you have the visible part, which is very, very important, and our eyes are sensitive to only this part of the electromagnetic spectrum, which allows us to differentiate and see things how they exist in nature. So UV rays and X-rays can have different sources, like an X-ray machine, radioactive elements which are found naturally or synthesized can emit X-rays and gamma rays. So this is the same thing. I'd like to just skip this part, which tells you about I would like to point out here, if you see the entire wavelength, the EMR, you see that the small portion here from 400 nanometers to 700 is only the visible part, which is very, very small, maybe 1/10 of the entire electromagnetic spectrum, which our human eye is sensitive to. So in remote sensing, if I go back to this slide, in remote sensing, we may not use X-rays, gamma rays for sensing. However, for remote sensing purpose, we generally use the spectrum, which is from ultraviolet to radio waves, going through the visible part, infrared, microwaves. So ultraviolet, why is ultraviolet important? Is it very significant in remote sensing, or it has limited applications? For example, the ultraviolet portion of the spectrum has the shortest wavelength that we can use basically in remote sensing. And it is beyond the visible part, which is just beyond the violet portion of the electromagnetic spectrum. You must be amazed to know that some of the Earth's surface materials, some of the rocks and minerals, I think we also read in our geology classes, can be very, very fascinating due to the fact that these minerals are fluorescent. So when you subject these rocks and minerals with UV radiation, they emit visible light, which is quite a magic of nature, and can be used to detect minerals on the Earth's surface. But the application of UV radiation in remote sensing is limited when compared to the rest of the electromagnetic radiation, which we will be discussing in the next slides. So the visible part, as I've already said, that the visible part is what our human eye is able to sense. It's basically from 0.4 to 0.7 micrometers, and so it is basically divided into seven colors. We all know that when you pass white light through the prism, it gets reflected into the VIBGYOR. We all are aware of it. So this is one of the most important part of the electromagnetic radiation, which can be used for remote sensing purpose. Well, in VIBGYOR, the red has the longest wavelength, and the violet has the shortest. And these, the RGB, which we call the primary colors, are which gives the concept of colors, and different other colors can be synthesized by mixing these primary colors. So these the electromagnetic spectrum. If you see the wavelengths of the red part of the electromagnetic visible electromagnetic radiation, it ranges from 0.6 to 0.7 micrometers, whereas violet ranges from 0.4 to 0.40 to 0.44 micrometers. Then comes the infrared. Well, we should be always careful when we are looking into infrared, because it has two categories that infrared is basically divided into. But if you see the broad range of infrared, it is approximately from 0.7 micrometers to 1,000 micrometers, which is 1,000 times the visible portion. So if you remember, the visible portion is from 0.4 to 0.7, whereas this is from 0.7 to 1,000 micrometers. Well, the infrared region can be divided again into two categories. One is called the reflected IR, and one is called the emitted IR. What is reflected IR? Anything which is falling on a surface and is reflected back, and that thermal energy is called reflected energy, and it is also called the near infrared, NIR, and the thermal infrared is basically emitted energy. For example, when the sun illuminates a surface on the ground, it heats up the body, it heats up the surface. But once the source of illumination is removed, the heat energy that the Earth's surface has gained over time is emitted. And that portion is called the thermal NIR and has wide applications when it comes to earth sciences. So as I said, the reflected IR is from 0.7 to 3 micrometers. It almost behaves like the visible part. And the thermal IR, which is the emitted portion of the IR radiation, the thermal IR is from 3 micrometers to 1,000 micrometers. Then comes the microwaves, which is again what can be used for earth science applications. Microwave has a wavelength of 1 millimeter to up to a meter, and it covers longest wavelengths in remote sensing and can be used for multiple applications like radio sounding and microwave data analysis, passive remote sensing, etc. So we are now done with, we are now clear that which part of the electromagnetic radiation can be used to sense the objects on the Earth or any surface on the Earth. But there is an important concept called the concept of atmospheric window. Well, this is how I would like to explain you in a very simple words. For example, imagine the atmosphere. Imagine the atmosphere which is around the Earth's surface to be a window, like you have the window in your houses. For example, if you close your windows, you will stop the light coming inside the room. And when you open your window or the curtain which you have in your windows, you will allow the light to come inside your room, which will illuminate your room and make it bright. In the same way, the atmosphere acts like a window, but it depends which window is controlled by what. There are several gases in the Earth's atmosphere. We all know that the major component of the Earth's atmosphere is the nitrogen gas. It is followed by carbon dioxide and oxygen. So here, if you see the window, this is how it looks like. So on the top, if you see my cursor, from the X-ray to the radio waves, you see that the ozone is basically not opening up the window to the X-rays and the UV rays. So what it is doing, the ozone which is present in the upper atmosphere, or the molecular oxygen which is there in the upper atmosphere, is not letting the UV rays to pass through it. So this is basically closing the window for UV rays and X-rays. But if you see the visible part of this, so it is almost, the window is open, and if you see the fraction of radiation which is blocked, it is minimal, only this part of it, which is very, very minimal. This is because of the molecular oxygen, which basically blocks a certain part of the visible portion, but majority of the visible part is allowed to enter the Earth's surface. Basically, the window is open. So none of the atmospheric gases are trying to block this visible part. And that is why we are able to see things. Whereas, in infrared portions, we have the water and the carbon dioxide playing a major role in controlling these windows. If you see, these are some of the windows in the infrared region, which almost is least blocked, whereas some of these are basically peaks because of water. And one of these peaks, I'm not sure which one, is because of nitrogen. So I'm sure the concept is clear to you that the window is basically dependent on who is controlling it, and who here I mean the gases, the atmospheric gases, whether it's ozone, carbon dioxide, and so on. But the radio waves, it's completely transparent. If you see, radio waves can reach the Earth's surface without being obstructed by any kind of atmospheric gases, which is responsible for its absorption, reflectance, and transmission. So this basically tells us, why did we discuss the concept of atmospheric window? This basically tells us which portion of the electromagnetic radiation is reaching the Earth and is least blocked, so that we can utilize these electromagnetic radiation in remote sensing applications. Now, a very, very, very interesting slide here. This is a very common slide where you will see in every remote sensing book, which tells you the reflectance curve of different land covers which exist on the Earth's surface. So what we see here is the x-axis here shows the wavelength in micrometers. The y-axis shows you the reflectance, right? So, and what are these lines? These are called the spectral response curve. Each of the object on the Earth has specific response to the electromagnetic radiation at specific wavelengths. So what do we see here? You have clear water, you have dry soil, wet soil, vegetation, turbid water. If you see, all these curves are same, all are different. Why? Because they are behaving differently to the electromagnetic radiation which it is interacting with. So for example, if you try to see my cursor here, the dark blue line is showing you the curve. It's showing you the curve of a clear water. What do you see? The clear water, most of the reflectance happens in the visible part, in the visible part of the electromagnetic spectrum. But as we move towards the NIR, the near infrared portion, it gets totally absorbed and reaches up to a point 0. If you see my cursor here, so the reflectance is almost 0 when it comes to clear water. At the same point, just look at the dark green spectral curve here, which is the curve of the vegetation. So what does it say? So it says that, at the NIR portion, the near infrared portion, there is a spike. There's a lot of reflectance. Whereas there is some absorption here in the visible portion, but most of the NIR portions are reflected. So now, the next slide is quite interesting. It's a question for all of the participants here. And I want you to answer that maybe through email or through maybe by the end of this session. I think we can have a question answer round where I think I can ask few of you to tell your answers to me. So now, if I ask you that how would you, if you were given two spectral curves, like the clear water and the vegetation, which portion of the electromagnetic radiation would you use to differentiate them? So here is a quick question to all of you. The question is, what is red and black color represent here on the ground? So on the left, you see an image. It is a satellite image. It is a false color composite image. False color composite image meaning that it is not truly representing the color, the natural color of it, but it is an NIR image. So my question is, what is red and black here? What does it represent? So I'll give you one quick minute to think, and then if you like to have a look into this slide has the answer. So quickly have a look into the NIR portion, which is the near infrared, and then let us go back to the next slide where you'd be able to answer this. So let me give you a hint. This is the portion where we are looking at. If you are looking into my cursor, this is the point where we are looking at. So, well, I'm not sure if the answer is in just the next slide or I've put it at the end. If it is the next slide, I'm really sorry, I'll have to reveal the answer. So I'm not sure what all the participants might be guessing right now. So let us look, what does it represent? So I said that it is an NIR image. It is a near infrared image. So if you go back to your slide, what do you see? Near infrared has the maximum reflectance in the NIR portion, right? And it is almost absorbed by water. So here, what do you see? A black color here. The entire EMR, which is falling on that water body, is getting absorbed. Whereas, if you see the surrounding areas, which is red and bright, that means that the NIR portion is getting reflected. So what do we mean? We are specifically referring to these two curves, the dark green curve here and the blue curve here. One is the water and one is vegetation. So if you see, this is how it will look like. This bright ones are the vegetation, whereas the water body appears to be black because it absorbs all the near infrared which is falling there, and vegetation reflects it. Okay, so we are quite familiar now with spectral response curve. So what is spectral response curve? It is nothing but it is the reflectance versus the wavelength of different materials. So let us see how these, it is, if we go to this slide, these are typical to clear water, typical to vegetation, or typical to dry soil or turbid water, but it can vary with a little difference. If we see these slides here, what do we have? In the first slide, we see the spectral response curve of different types of vegetation. Say, for example, the green is showing the grass, the blue is showing a walnut tree canopy, whereas the violet is showing you a fir tree. So what does this mean? It means that remote sensing allows you to differentiate not only between water, vegetation, or discrete objects on ground, but can also help you to distinguish between subcategories of each broader category. So all these are vegetation. So grass is also vegetation, walnut tree, a fir tree, and a dry yellow grass. All of these fall in the broad category of vegetation, but their spectral response is different at different wavelengths. So grass is having the maximum reflectance in the NIR portion. As we go down, a yellowed grass is having less reflectance in the NIR portion, right? Similarly, when it comes to soil, you may have dry soil and the wet soil. If you see my cursor here, the orange spectral curve is telling you about the reflectance, how the dry soil will behave and how wet soil will behave. So reflectance basically goes down a bit after almost the entire electromagnetic spectrum when we compare the dry soil and the wet soil. Now again, coming to, you would be amazed to know that remote sensing is even capable of identifying definite crops on the ground. So if you see the graph here, it tells you about the difference. For example, sunflowers, soybeans, corn, potatoes, grass, wheat. You can differentiate all of these using remote sensing images based on their spectral signatures each of these have. So I'm quite sure now it's quite clear that spectral response curves are important to distinguish things, not even in a broader category, but also in the subcategories or minor categories as well. So moving forward, we have in remote sensing is called the sensors. As I've already told you in the first two slides, the sensor is what? Is nothing but the device or the component which is basically trying to analyze the reflected signals, trying to process the signals and give us an output which can be used for its application. Now, sensors, remote sensing can be broadly categorized into two types. One is active remote sensing, the other one is called passive remote sensing. I'm sure most of you are familiar. What does this mean? Active, let me quickly define you. Active remote sensing is nothing but when the sensor, if you see the sensor is the source of illuminance itself. So what in an active remote sensing, what happens? That the satellite, the sensor sends a signal, it receives the signal back. So it is both the source and the acceptor of the reflected energy. So this is called active. What is passive? Passive is you have another source, but you have a different receiver. So when the source of energy is different, it is called passive. When the source of energy is there in the sensor itself, it is called active. So both of them have their own applications in remote sensing, which I think we will be discussing in our further slides. So what of sensors? So do not confuse with a sensor with a satellite. Sensors are not satellite. Satellites are platforms. Platforms are the bodies or the instruments that that actually host the sensor. It holds the sensor. The platform carries the sensor. Sensor is not the satellite. So if you see, there are two different. They're differentiated as sensors and platforms. Sensors are a device that records the EMR, and the platform is the carrier of the sensor, right? So we are all aware of the Lancet mission. I think most of us who are geography students or geology students, or the audience who are familiar with geology or geography must have heard about Lancet images or might have worked with them in your research. Lancet is a series where it's a satellite. Lancet is basically a satellite, which means that Lancet is the platform, whereas each Lancet mission from 1 to 8, and I think in 2021 Lancet 9 is going to launch. And what do we have is that each of these Lancets have different sensors which they carry. For example, MSS, ETM, OLI, TIRS, all these are sensors which are on board of the satellite. Now comes the concept of resolution. So what is resolution? So in remote sensing, there are basically 4 types of resolution. One is called the spatial resolution, then comes the spectral resolution, then comes the temporal resolution, and then comes the radiometric resolution. So the concept of resolution is really important when we are looking into its applications, because each of them might have their own use. So in this picture, what do you see? What do you see on the top right? What do you see? You see maybe a road going, or some houses, right? And you see some canopy, which is there here, right here, quite clear. These are trees, these are buildings, this may be a road, quite visible. Now let us go back, let us go to the next image. Quite good. You are still able to distinguish between the houses, the canopy, the roads. Then come to the next slide. It is a bit blurry. I mean, you are able to distinguish between the things, but it seems to be a bit blurry here. Now, as we come to the 5 by 5 meter resolution, well, here it kind of getting difficult to identify, to differentiate between the canopy and the houses at the upper portion, at the upper part. So mostly at this part, if you see, the houses quite is looking like the canopy itself. But if you come to 10 by 10 meter resolution, I mean, nothing is visible. You just see some linear feature here, some white objects, some different reflected bodies having different pixel values, but you're not sure about what this image is representing on the Earth's surface. 20 to 20, there is no way that you can distinguish or identify anything. You have just white pixels, black, gray pixels. You don't know what is there. So, and as you go on 80 meter by 80 meter, so it's basically looks like some some color variations. You don't know what is it. If you just show it to a random person without showing the first picture, no one would be able to recognize what is there behind this or what is it representing. So what does this mean? That different resolutions can be used for different purpose. For example, when we are looking into smaller things on ground and we want to distinguish between smaller objects on the ground, we need to have a higher resolution image. But when we are looking into regional scale, where minute details doesn't matter to us, where we want to extract information about something which is regional, or maybe a 500 meter by 500 meter pixel would not make any difference, or even if it makes a difference, would an analyzer would not need such minute discrete details. So in that case, we would be using a low resolution image. So this is how it is done. So basically, larger is the pixel value, lower is the resolution. So just keep in mind that higher is the pixel size, the lower is the resolution, and vice versa. Now comes the second resolution, which is called the spectral resolution. How is it defined? The spectral resolution is defined the ability to resolve the spectral features and bands into separate components. More number of bands in a specific bandwidth means higher spectral resolution, vice versa. So let us look into this. I know definitions are always, illustrations are always better than definitions. So if we look into this, what do we have? We have multispectral. Here we have, what do you see? That each of these layers is telling us information about some part of the electromagnetic spectrum. So excuse me. So what do we see here? That each of these layers are telling you a certain part of the electromagnetic radiation. If you compare these layers on the left to the layers on the right, what is the difference do you see? What is the basic difference do you see? The basic difference is the number of layers. If you have 10 layers here, you might have 1,000 layers here. If you have 5 layers here, you may have 50 layers here. So What does this mean? That each of these are thicker, and if you see these layers are thinner, but you have multiple numbers of them. But these are broader, but you have fewer of them. So what happens? These are giving us discrete data. For example, if you see the lower graph, you have discrete data. Each of is giving us a discrete. But here, what you have minute details. Minute part of the electromagnetic spectrum, which is continuously given. If you see here, if it is the reflectance in the y-axis and the wavelength in the x-axis, if you differentiate these two graphs, this is point data, or maybe quite discrete data. This is continuous data. So all these comes in two branches. One is called the multispectral remote sensing, which is mostly deals with discrete and broader wavelengths. And here it's continuous, which is called the hyperspectral remote sensing. Both of them have their own applications towards sciences, which we will be discussing in our coming slides. I'm really sorry for this slide. This is quite blurry, but still, I'll try to just explain you this illustration. If you see, there are three continuous spectra, which was shown. One is low, medium, and high. What is the difference? If you see from far, it almost looks similar to you. It is almost the same. You have the same crest, you have the same troughs. But if you see carefully, the higher spectral resolution have more details. There are minute troughs and crest even in the broader valleys. If you see these valleys here, if you see this valley, if you see the higher spectral resolution valley, you may see smaller valleys and within the bigger valley, which means that these are giving you discrete data and giving you more detailed data, right? Now coming to the next, temporal resolution. This is one of the most interesting part of remote sensing, where we can go back in time to see how certain things on the Earth's surface, or certain processes which is going on the Earth's surface, or can be viewed back in time. So what does temporal resolution mean? Is that the frequency at which the image is recorded at a point. So we know that satellites are revolving around the Earth all the time, and they're recording the Earth's surface at a point, and it comes back to the same point after a certain amount of time. So this is called the repeatability of the satellite. So when it comes to a certain point, it will go around and come to the same point. It might come back to the same point. So the number of times you have number of data sets of a single point. So the time difference between one set of data till the next set of data is called the temporal resolution, the frequency, So let us look into this. For example, you have, say, a repeat cycle of 16 days, which is shown on the top, and you have a repeat cycle of 11 days. What does it mean? That this satellite is coming to a single point every 16 days, and it is looking into try to capture one portion of the Earth every 16 days. But whereas this is trying to capture a particular point at the Earth's surface every 11 days. So what do we mean? That we will have more frequent data here in the lower part. If you see the same time frame, we have the red dots 1, 2, 3, and 4, where we have the blue dot as 3. So the number of observation which was done by the 16-day cycle satellite has less number of data as compared to the 11-day cycle data. So this is basically more beneficial in the 11-day because it is giving us more frequent data when compared to if we are trying to look into changes which happens in a shorter time scale, so change in the vegetation or change in for example, would like to see the temperature, how it is changing, you may have to have shorter temporal resolution. high temporal resolution, which means that it visits the same place quite frequently. Now comes the radiometric resolution. This is a last resolution that we are interested in remote sensing images. This is nothing but the sensitivity of the sensor to the magnitude of the received electromagnetic energy, and it is given in bits. We all might have heard about 16-bit images or 8-bit images or 10-bit images. You know, what does that mean? That the range, the range in the reflected energy will have a value from 0 to 4 in a 2-bit image. Whereas as we go from 6-bit to 8-bit to 10-bit, the range increases from 63 to 255 to 100. So what does that mean? This radiometric resolution, the higher the radiometric resolution, the better the image would look and would help us to differentiate things on the surface of the Earth. If you see these two images, same image of the same location, but a low radiometric resolution and a higher radiometric resolution where the pixel values are stretched over different ranges of the different range. So let me quickly go through the I already said about multispectral and hyperspectral in my previous slide. What was to recall again, what was multispectral? Multispectral was nothing but when you have discrete layers, less number of layers of each of these layers representing certain portion of the electromagnetic spectrum. Whereas if you have number of layers with minute or shorter range of each of them is given by hyperspectral. And the panchromatic is nothing but it is a single layer. Each of these can be given as a single layer, which is a panchromatic, which is nothing but is showing you only one particular portion of the electromagnetic spectrum. So this image is giving you from 0.7 to 0.4 to 0.7, just one image. Whereas this multispectral can have energies reflected at different portion all through the electromagnetic spectrum. Hyperspectral again is a continuous record of reflected energy. So same here, if you look at this in a visual representation, what you'd have, you would have a multispectral where you have less number of bands, hundreds of bands in hyperspectral, thousands of bands in ultraspectral. So number of bands are increasing, which also helps us to have different applications of all these bands. Let me quickly skip this. I think I've explained this before. Here again, the comparison of the spectra. If you see, this is very, very rough spectra, and we do not have a continuous spectra like we have in case of more data or a hyperspectral data set. So both multispectral and hyperspectral have their advantages and disadvantages. So what multispectral data can do? Actually, multispectral data can discriminate materials, but hyperspectral can identify material. For example, a multispectral image can tell you, if you're looking into geology, if you're looking into certain rock types, it can tell you about whether it's a sedimentary rock, whether it's a sedimentation happening in a certain portion of the ground, whether it's hard rock or any exposed outcrop. You may use multispectral, but in order to identify the minerals which are present in the rock, or maybe you want to identify the clay minerals which is present in the sediments, you might be using a hyperspectral image, because this is giving you more micro details of the reflected energy. Similarly, it helps you to identify. Hyperspectral can be used to identify when many materials are mixed together, which is very impossible when you're using a multispectral, which will help you to discriminate between things, mixed materials, where hyperspectral can help you do that. So this is the same thing. So the working principle. So if you see here if you see the extracted portion, this is the soil at one portion the water and the vegetation. So each of these layers, if you convert them into electromagnetic spectrum response curve, this is how it would look like. You have mostly continuous data. Now, how is it applicable in geology? So I think geology people here in the audience, I think you'd be interested in this. We have been now talking about hyperspectral data and its comparison with the multispectral data. So in geology, what we have is different rock types, not categorized broadly as igneous, metamorphic, or sedimentary rocks, but again, we have subcategories. We have, in sedimentary rocks, we have clay minerals, we have different types of processes that forms the rocks, So here is an example how hyperspectral remote sensing can be used to identify the minerals which are present in the rock. So if you see here, again, the y-axis is giving you the reflectance, the x-axis is giving you the wavelengths. So what it is telling you, as we already have seen that the working principle that in hyperspectral we have continuous data, which gives us a continuous data. So this is a continuous data within the wavelengths from 0.5 to 2.5. And these are clay minerals, kaolinite, montmorillonite, and muscovite. Muscovite is basically a mica. And then what do we have? We see that these curves are behaving differently at different wavelengths. See, at wavelength 1 micrometer, muscovite has the least reflectance, while kaolinite has the maximum reflectance in almost the entire part of the electromagnetic spectrum. So when you are trying to differentiate these, it is actually not possible by looking into just the entire electromagnetic spectrum, but we will have to look into these troughs, which are basically deep troughs. You see the T points which are marked into T. I'm sure it's visible to you. So these are the troughs which is marked by T. So in all the cases, these troughs would be different and will shift from and would behave at this particular wavelength. And if you see these peaks, so these are typical of kaolinite. These troughs are typical of kaolinite. These troughs are typical of montmorillonite, whereas these absorption valleys are typical of muscovite. So when you're trying to correlate an image, hyperspectral image of a ground which has mostly clay minerals and micas, you would like to look into the spectra to differentiate between the minerals. Now coming to the carbonates. We all know what are carbonates. Carbonates, again, is a type of sedimentary rock, can be of different types, and it has mostly the CO carbon-oxygen bond, and you have calcite, dolomite, magnesite, and siderite as the example taken in this spectral response curve. See, all of these, again, if you see what I've told you in the previous slide, have their own way to behave to particular wavelengths of the electromagnetic spectrum. Calcite is showing high reflectance in almost the entire wavelength, entire series of wavelength. Now, interesting thing is between magnesite and dolomite. What do we see here? Dolomite at 0.5 micrometer is showing high reflectance, whereas it is the opposite. As we go down in the electromagnetic spectrum to a higher wavelength, in dolomite, the reflectance basically changes. It comes down, whereas in magnesite, it comes up. But this is what will make you differentiate between dolomite and magnesite, but rather the point where these valleys occur. All these valleys are slightly different. I'm sure the scale is not very, but if you zoom in, these will have their own location in the electromagnetic spectrum, which will help you to identify these carbonate minerals on the ground using hyperspectral images. Well, again, coming to silicates, SiO2, we all know SiO bond. In geology, we are fond of these two elements, silicon and oxygen, because most of the Earth's rocks are composed of silica. So if you see quartz, they look really beautiful. If you have the pure silica, SiO2, you have different types of rock, like you have a muscovite, which is mica. Olivite is a mineral, rock-forming mineral. You have hornblende, you have augite. All these are rock-forming minerals, and each of these minerals have their own specific signature. And you see that the arrows which are marking the crest of the reflectance, these wavelengths are shifting from lower wavelength to higher wavelength as we come from quartz to olivine. But whereas if you see here, we are basically, orthoclase has no signal. Orthoclase basically is starting from here, from wavelength 12 micrometers. And so this is basically shifting towards the right. So the troughs are shifting towards the right as we move from quartz to olivine, whereas the crests are moving a little towards the lower wavelengths. So this will help you identify between the different rock-forming minerals on the ground. Well, again, these are silicates before. Now we'll look into the non-silicates, which is calcite taken as an example, calcite, apatite, gypsum, hematite, and kaolinite. Again, the same. Here we would look into the troughs and minerals to identify them. I'd like to skip this slide because we kind of understood the concept here. Some of the spectral, hyperspectral satellites, which is there and is giving us data for free, and you will be able to download it for your research or any kind of report that you are planning to write very soon or currently working on, is basically Hyperion, MODIS, PRESS. These are a few satellites which is making hyperspectral data free for use. You may download it from different websites which it makes available. Now, the advantages of remote sensing. We've discussed enough about remote sensing, how it works, spectral response curve, its resolutions. Now coming about the advantages, we see that, well, advantages is that it helps us mostly about global coverage. It has global coverage. We can monitor the entire Earth. Any place on the Earth we'd like to have an information, we can have it by sitting at any other point in the whole world. Again, a synoptic view, it's more of, if you like to have a comparison of a larger area and see how is the dynamics or how is the properties changing. You may have a synaptic view for comparison, and you have a repeatability, which means that you have data coming in all the time, and you can compare the data from now, which is collected today with the one which is collected in the past, and it is cost effective. It's not very expensive. Well, many of the data is free for use. Landsat, for example, is moderate resolution images they provide, which are free to use. I'm quite going towards my end of the PPT. I still have quite a lot remaining, but I'll try to finish as fast as possible. I'm sure if I'm not making you sleepy or bored, if you just sleepy, I can give you 1 minute to just wash your face and come back. I think that would be fine, or maybe drink a sip of coffee. But okay, let us quickly go through the application domain. What we have is physical sciences. You see that mostly remote sensing is basically falls on the physical sciences domain, but remote sensing can also be connected to biological sciences, social sciences, using other means like geographical information system. So this is where it comes in play. GIS, as my talk says, it is remote sensing and GIS application in earth sciences. So here, GIS plays a major role in where it is trying to relate remote sensing with the other branches, maybe say it is biological sciences or cartography or surveying when it comes to social sciences, and so on. Well, the applications are quite vast. We just cannot be put into a single slide. It starts from agriculture, land use, land cover mapping, forest, weather, water, geology, disaster, ocean planning, whatever you would like to do or study, based on the Earth's resources and satellite data, and you'd like to see the resources, sustainability, remote sensing helps you do all of these in the best possible manner. So environmental changes. So how remote sensing helps us to see about how environment is changing. We know that with the climate changing over the years, over the past few decades, and the temperatures rising, we see several changes occurring on the Earth's surfaces. For example, change in the ocean currents, change in the coastal regions, sea surface temperature, which is again related to ocean currents. If you see that sea surface temperatures can lead to upwelling or downwelling of ocean currents, which may lead to ocean currents like the El Nino and the La Nina, which happens in the oceans. Then coastal bathymetry. Sometimes, in the coast, what does bathymetry mean? My bathymetry is nothing but, I think we have a question. So maybe we can have the questions at the end of this session so that I can finish it soon, and then I can have a question later on. So yes, let us go back to the next slide. So tropical deforestation. Deforestation is another major cause of forest degradation, or maybe pollution, and several pollution that happens in the ocean as oil spills, thermal pollutions because of radioactive matter, particulate pollution, which happens because of the industrial waste which is discharged into the oceans, and so on. Now, applications of remote sensing in vegetation and agriculture is that it helps in monitoring crop yield. For a country like India, where we have the second highest production of wheat and rice and other crops, and most of the economy and most of the sector depends on agriculture. Is how can we use remote sensing here? Maybe do some modeling to monitor the crop yield, and then the quality of the crop can also be monitored using remote sensing. Then the benefits of remote sensing here would be the soil status, the monitoring of the soil status, and decision-making process, which I will be coming on our later slides. Some very interesting slides coming up. I want all of you to stay awake. Well, this is what is important. Health. We know that it is important for us, but do we know that plants also have their health? Well, yes. Plants also have their health, and some plants are healthy, while some of them are unhealthy. How do we determine that? We look into the plants and we say that this is a dead plant. And when we see that the leaves are quite green, we say that, okay, this is a healthy plant, right? That is what we look like. But what if the color of the plant looks similar and it's quite green, but will you be able to say that it is a dead plant, or is it unhealthy? Well, not very discreetly or very with confidence, but yes, remote sensing can. What do we have here? On the top left, you have a green colored tree where you see the blossoming leaves here, whereas on the right, you have an unhealthy tree where the color of the leaves have almost faded and looks like a tree which appears to be in autumn season. What happens here is that when the electromagnetic spectrum or electromagnetic energy strikes these leaves or the canopy where these leaves are present, they have different behavior. And this behavior of these vegetation helps us to identify whether a vegetation or a tree is healthy or unhealthy. So for example, in a healthy tree, let us go back to our primary classes. Let us go back to what we studied in our school. Our teacher told us that, photosynthesis, where does oxygen come from? All that we have studied in our preliminary school. Photosynthesis is a process where the plants make use of the pigments like chlorophyll, which is present in their leaves, to produce oxygen. And during the process, what it does, it tries to take the energy from the visible part of the electromagnetic spectrum. Whereas if suppose a tree is no pigments, the pigment levels are low. For example, a leaf may have two types of chlorophyll, chlorophyll A and the chlorophyll B. Each of these have their specific characteristics of absorbing wavelengths of 0.45 and 0.47 micrometers. So for example, if the chlorophyll content has gone down in some of the trees, you see that the visible part is more reflected than a healthy tree, because the pigment is not able, the amount of pigment that unhealthy tree has is not able to absorb all the visible light which is falling on that. So this can be basically used. This principle can be basically used to find out the health of the vegetation by using some indices, which is called one of the indices, which is called the Normalized Differential Vegetation Index, NDVI, which is given by the formula NIR and red, because these are the two principal components of the electromagnetic spectrum, which we are looking at to differentiate in healthy and an unhealthy vegetation. So here in the bottom, what do you see? You have a dead leaf, we have a stressed leaf, we have a healthy leaf. You know, this stressed means this leaf is exhausted, almost going towards the dead level. And then what do we see? We see that in a healthy leaf, the NIR here has the maximum reflectance. But as we go to the dead levels, the NIR reflectance reduces quite a bit. So this is what makes it different, and this principle can be used. These bands, this portion of electromagnetic radiation like NIR and red can be used to differentiate the healthy vegetation and vegetation. Well, this is some advanced agriculture coming out here. Precision agriculture. So what do you mean by precision agriculture? Well, these images look very fancy and looks like some color palettes. Some color palettes look fancy, but you know, these have definite meanings and very useful when it comes to agricultural applications. What do we have here? This is nothing but, this is telling you the agriculture, the plants, these are vegetation, these are nothing, these round ones are nothing but vegetation in definite shapes. If you see, this is the ground, and if you apply this formula, you would get an output like this. So when you're using NDVI, where you're using the NIR and the red bands, the output would be in a scale from -1 to +1. What would a minus value would tell about an unhealthy vegetation, whereas higher values of NDVI would tell a healthy vegetation, the condition of the vegetation. So what happens in precision agriculture? Precision agriculture is a new technique where, you know, we use remote sensing to identify those specific zones which needs attention in agriculture. For example, if you see here, if you zoom into this part, if you zoom in this to this part, what do you see? That one portion here is showing low NDVI values, you know, which means that this part needs attention. So I'm almost going out of time. I would rather stop in a while. So let me quickly go through it. So I'll just skip my slides here. I will show you some of my field experiences which I did during my visit to different places. So here it comes. So some of my research I'm really sorry that I had to skip so many slides. If I get another chance, I think I would love to continue with that. But right now I'm short of time. I would like to wind up by telling you some of my research outputs, which I've been doing from the last 5 years or so. So, hills of tragedy. We are all aware of the 2014 Kedarnath flood that happened, which washed away the Kedarnath settlement, killing around 4,100 people. Many foreign people who have come to explore our country went missing in this flood. It was a tragedy. It was all over the news. And if you see that, in fact, the Himalayan mountains to be a scenic beauty can also be tragic like this. So there were several articles that were published that it damaged a hydropower station, several buildings, and so on and so forth. These are some of the. So what we did basically is we tried to, after the incident happened, we tried to look into what happened. If we know the story about it, it was nothing but it was a flash flood which happened because of a cloudburst event. Because of the cloudburst event, there was a glacial lake which was known, it was called the Chorabari Lake, and the lake had failed. It had failed and leading to the water gushing down and washing away the entire settlement in Kedarnath. So after that incident, we tried to look into all these lakes that are present in Uttarakhand. So what do we have? That the number of lakes and the area of lakes are going up from 1960 to 2000, almost 2018. What do we see? That the area of the lakes are going up. I mean, they're growing. So what does it mean? As the lakes are growing, the hazard levels are also going up, because the larger is the lake, the more water it carries, right? And in case of a failure event, it would have more impact. So I'll quickly skip this slide and show you what we did. So this is how it looks like. First the lake would look like small, then it would grow in 1996 and 2001 and 2015. So you see the lake has been growing, and this is because the glacier, which is it is receding, and because of that the glacier lakes are growing in front. So we went to the field, and this is what we have published in the journal called Natural Hazards in Springer. Here, what we did is, when we went to the lake, we went to another lake which was called the Satupant Lake, which is very adjacent to the Chorabari Lake of the 2014 disaster. And then these are some of the measurements we took along the channel. We took some measurements on the lake and implemented all these GIS data. These are nothing but I'm collecting GIS data and implementing all these GIS data in modeling techniques like hydrodynamic modeling, using different models to find out the different impact of flood here. So this is how the results look like. So when we try to model these, we see that what is the flow heights along the channel, what is the flow velocity along the channel, what is the inundation that if in case a lake outburst happens, what would be the effect in the downstream region. This is how we model and express our results. This is nothing but, again, both remote sensing, GIS, and hydrodynamic modeling clubbed together. So this is what happened. This is me with the GPS rover, as I've already shown before. This is the flood that damaged the hydropower station, and I'm right next to the dam taking my readings. So I'll quickly play one of these. If you see, if I play these, how the flood wave will arrive, the blue water coming up from top to the bottom. So this is how we model the floods that happen. Another, in 2018, I was in Iceland. I got a fellowship where I could visit Iceland. My mentors from IISc Bangalore and IIT Roorkee has given me the opportunity to go there and explore this beautiful place. I'm sure most of you know where Iceland is. It is basically in European country. It's a form of an island, and it's a beautiful place. So I went there and I studied one of the flood that happened in 1967. So let me quickly take you the place. So I'm going to take you where I did my study. So, oh, sorry. So this is where Iceland is, how it looks like. And I was doing my study at this place. This is the Steinsold Glacier. And there was a flood happened back in the 1990s where it washed away, the flood propagated through this channel and washed away several villages here, which is present along the coast, and had several impact downstream, washing away several bridges on the way. And it was quite a bit of an experience to have visited this place, which is full of earth science mysteries, volcanoes, and several other geological monuments. Let me go back to my slide again. So this is how the flood propagated. We tried to see that, okay, there was a landslide that happened, which led to the outburst of the lake. The landslide fell off on top of the lake, which led to the flood. We used remote sensing data sets to find out the volume of the landslide which fell on top of the lake, using differentiating to them pre and post digital elevation models to find out what is the volume. And this is how it looks like. This is how I modeled the event. You see that it started from the bottom right corner towards the top left, and this is the inundation that the flood caused. And if you see how the modeling results look like, this is showing the water velocity plots, and if you see how particle movements are happening in case, and the arrows are showing the direction of propagation at each parallel side. Oh, now I'm almost in the end. So I told you to have a look into the slide that I started with. It was the Brahmaputra River going across the city of Guwahati. So this is Guwahati in 1984. So I would like you to pay attention along the river. This is the Brahmaputra River, and also have an eye on the box here, which is Guwahati city, and see how it has changed over the time. And it was quite fascinating to see how things change in nature. So let us go forward to 1994. If you see 1984, 1994, see the difference here. The river has been quite a bit changing because of the sedimentation processes. If you see Guwahati, if you see there are less number of buildings. If you go to 1994, you see quite a bit of settlements coming in. Then let's go to 1999. So 1994 to 1999, what do we have? We have, again, the river changing very rapidly. We have more settlements coming in here. If you compare Guwahati here, you see that the settlements have been increasing every year. This is 2010. Again, a very dynamic river. Enough sedimentation happening, leading to its braided nature. 2019 is what we are today. You see that Guwahati city is full of new settlements. A lot of buildings have the city have expanded. If you have seen the previous images, the expansion of the city was limited up to this extent, but we see that the Guwahati has been expanding. And this is because of the new technology, the urbanization that is happening in Guwahati. So this is it. These are some of my research. You can have a look at my papers, which I published. So I work on basically flood modeling using remote sensing and GIS and hydrodynamic modeling techniques. So before I stop, I have a message to all of you. This is a new initiative which is taken by Dr. Prashanta Goswami, his own honorable chairman. This is called the Assam Conservation Trust. It's a TACT, very new initiative to protect the heritage of the state for sustained efforts to conserve and enrich the heritage of Assam, and blending progress and conservation. So this is I'm really happy to be a part of this. I recently had the first meeting with people, Assamese people or other people, mostly the Assamese community spread across our country from different places. And Dr. Prashanta Goswami, who is the founder chairman of the Institute of Frontier Science Application, IFSA, and he has been a lead author in the IPCC report, and he has been very enthusiastic in moving this forward as an initiative in 2020. So I think the participants here, you being, whether being Assamese or not, we are always should put our fourth interest in looking into conservation of our nature, whether it's culture or food or heritage or whatever it is. A region doesn't matter, the nature matters to us. So whether you're Assamese, non-Assamese, all of you are welcome to be a part of this TACT organization. If you are interested, you may write your interest to the email ID that is given below. And if you need further details, you can email me. I can add you, and I can ask the members, the senior members in the TACT Foundation to add you and have your contribution. Well, thank you all for your patience. You may reach out to me. I've given you, this is my email ID, my name with a dot in the middle. And if you have any doubts, you may write to me. I can answer your questions back. Thank you all and all. Have a good day ahead. Thank you.
Thank you so much, Dr. Ashim Sattar. That was
Thank you.
a really awesome presentation on your part.
Okay.
I think you have included all possible points,
Thank
whichever is possible to go online. Yes.
Right. Thank you so much.
Not only students, we teachers are also very much benefited by your presentation. Now it is time to deal with the questions which are coming in the chat box. Actually, we do not see much questions there. There is one interesting question. It is asked by Jayati Brahma. She asked, what is precision agriculture? You mentioned.
What is precision agriculture?
Yeah, precision agriculture.
Okay, precision agriculture is it's a new technology development in the field of agriculture. Basically, primitive technology, primitive methods of agriculture used to have manpower mostly looking into the fields, looking into the crops individually over a larger area, which becomes very difficult, and we do not have target specific. For example, when you have say different crops or the same crops in different locations or in the same location might have different properties. For example, the slope of the ground may be different, or the illumination from the sun can be different. So in that sense, we need to specifically target those plants which are under stress, which are basically dying or are less deprived of the nutrients. So what does this technique do is that they try to identify these using remote sensing technology or GIS-based technology and target only those crops which are under stress rather than looking into the whole field. And it has less manpower needed, more of a technology-based operations using UAVs and robotized tractors and so on.
I think Jayati, you got your answer. Now for the next program in the session, I would like to forward to Dr. Hafiz Muhammad Abdul Sahid to provide the vote of thanks to everyone.
A very good afternoon to all everyone. I, on behalf of Lakhimpur Girls College, take the opportunity to extend sincere and heartfelt thanks to Dr. Ashim Sattar for accepting our invitation for the webinar as a resource person. I take the opportunity to extend our thanks to Dr. Ashim Sattar for his lucid and very informative presentation and sharing his valuable time with us. Hope the participants will have a lot to take away from the presentation. I extend sincere thanks to our esteemed participants, without whose active participation the webinar would have not been a successful one. I extend sincere thanks to our principal sir, Dr. Surajit Bhuya, for his constant inspiration in organizing the webinar. I also extend sincere thanks to IQAC coordinator Dr. Bhupen Sutia for his cooperation. Last but not least, I express my heartfelt thanks to the entire team who is directly or indirectly associated in organizing the webinar, without whose helping hand this event would have not been possible one. Thank you. Now, I would like to request Dr. Bhupen Sutia to wind up the session.
Thank you, Dr. Sahid. I think you can hear me?
Yeah. You are audible.
Right. Thank you, Dr. Sattar, for being the guest, our guest today. And I, on behalf of Lakhimpur Girls College, as the coordinator of the internal quality assurance cells of this college, would like to thank you all, our resource person and participants, as well as the Department of Geography for organizing this beautiful webinar. And I'd like to inform you all that this has been our effort since the last 20 days. We have been organizing a series of webinars, and this was another successful webinar. Thank you all. And with these few words, I would like to declare that this webinar has come to an end. Thank you all, and have a good day to you all.